All right, let's talk about profit maximization. So in the last module, we learned about the relationship between output and costs. And now, given that the firm just faces a price, the profit maximization process is going to be the process by which the firm chooses what level of output to maximize profits. Well, that's where we're going, and let's just get there step by step. So let's start with a picture. In the upper diagram, we have a picture that contains a lot of elements we've seen before. We have quantity on this axis, and we have cost on this axis, but we are also going to put revenue into this picture. So the red curve is that short-run total cost curve we had last time. What we're doing now is we're adding in revenue. So revenue is this green line, and revenue for a competitive firm is just P times Q, just a ray from the origin. Now, why is it a ray? Well, it's a ray because P is fixed for the competitive firm, as we've been saying. So it's just a constant P times Q, and so it just comes out of the origin with a constant slope of P. Anyways, we can see profits in this picture. Profits are the difference. Profits are equal to revenue, minus TC, minus costs. So profits here are initially negative. So here we have some costs, but no revenue, so profits are negative. We move along, and profits do whatever they do. Eventually, we have profits that are pretty, if we were to produce at this level of output, we'd have negative profits. If we get to here, we'd get to the point where revenue actually equals costs. So if we were to trace down, we'd see that's a point of zero profit, and so forth. Now, as we were to continue, there's another point with zero profit, and somewhere in between, profits are this vertical distance here, somewhere in between, these profits are being maximized. So wherever we have the maximum vertical distance between revenue and cost, and these should be vertical lines, we would have maximum profit. Now, where it actually occurs is a point where this black dot is, and what's special is that the vertical distance is maximized. If we were to represent the profits down below, and the scale's not quite accurate, but we'd see that the purple line shows us profits. It reaches a maximum at this quantity Q star. Now, what can we say about this point, this Q star? It's pretty special. So profit is maximized when we've chosen a level of output, Q, such that, well, the following things are true. Maximum distance between TR and TC. The slope of TR equals the slope of TC. Another way to say that is to say that marginal revenue equals marginal cost. Now, why is that? Because marginal revenue is the additional revenue with one more unit of output, and marginal cost is the additional cost with one more unit of output. Now, one last way to say it, if you're a calculus buff, is that the derivative of revenue with respect to quantity equals the derivative of cost. But this last condition here, intuitively, just boils down to P equals MC for a competitive firm. So remember, for a competitive firm, marginal revenue just equals the price. So what we're saying is, in order to maximize profit, a competitive firm should choose the quantity so that MC equals P. Let's revisit this story in another picture. What's different here is that in the lower diagram, instead of having profit, although there will be a way to see profit, we instead have those average total and average variable and marginal cost curves that we recently derived. So I want to show you how to see profit in this lower diagram. As we already know, in the upper diagram, profits are vertical distance between total revenue and total cost. How about down below? Well, one thing that's new is we've put in this kind of dark red line, which is the firm's demand curve right at the price. So let's just call it D. And I can also note that this is at the price P, and it equals marginal revenue because marginal revenue equals P for the competitive firm. But in any event, how does this firm maximize profit? Well, remember, it wants to choose the quantity of output where marginal revenue equals marginal cost, or since it's a competitive firm, price equals marginal cost, and that's where that occurs. So here's the same Q star that maximized this vertical distance. Now how about profit? Can we see profit in this picture? Well, again, it was a vertical distance up here. That was pi. Down below, though, it won't be a vertical distance. Instead, it's going to be an area. Now how do we get that? Well, at this unit of output, Q star, The price is P. The average cost is right here. So this vertical distance here, P minus AC, is the, well, it's the average of profit per unit. And if we multiply that by the number of units sold, we get the profit. So how do we see profit down here? Well, profit equals revenue minus cost. So that also means it should equal revenue over Q minus cost over Q, all times Q. Well, that just equals P minus AC times Q. And indeed, here's P minus AC, and here's Q. So this green rectangle is profit. Let's revisit the question of profit maximization in this diagram. Up above, we have the same diagram we've been seeing. Down below, instead of just seeing a mountain for profit, instead we have average variable costs, average total costs, and marginal costs. Now, we talked about the various conditions for maximizing profit. One of them was a maximum vertical distance between revenue and cost, but the other was, or one of the others was, find the Q where P equals MC. Well, to do that in the lower diagram, we need to add in the demand curve, which is horizontal at the price, P. So there it is. We see the intersection of this demand curve, right, with the marginal cost right here. And so this Q star is the quantity where MC equals P. How about profit? Well, profit is the difference between price and average cost multiplied by the number of units of output. And so indeed, profit is this green rectangle in the lower diagram. And that corresponds to this vertical distance in the upper diagram. Now we get to one of the classic conundrums of managerial economics. What if price is below average cost? Should the firm produce? Now, why is this an interesting question? Well, when price is below average cost, that means profits are negative. So that sounds kind of bad. Well, let's think about it. Here's a picture of the kind of the lower type diagram where we have average costs, average variable costs, marginal costs. We have the quantity of output here, and we're measuring dollars over here. The one thing we don't have here yet is the demand curve. Well, let's put in a demand curve such that the price is below average total cost. So indeed, we have the demand curve crossing marginal cost right here. The question is, what should this firm do? Well, if it chooses the Q where P equals MC, it's choosing this Q as Q star. Now, what are the profits if this firm produces? Well, they're actually, there are profits, but they're negative. And why are they negative? Because price is below average cost. So that's the amount the firm loses per unit, that vertical distance. It produces Q units, Q star units, and so this forward hatched region is the losses if the firm produces. We still haven't answered the question, though, should the firm produce? To answer that question, we have to compare the losses if the firm produces to what the firm experiences if it does not produce. Now remember, in the short run, the firm is stuck incurring its fixed costs, so it has losses even if it does not produce. And the question is, how do those losses compare to the losses if it does produce? Well, we can answer that. Turns out the losses if the firm does not produce equal both the losses if it does, as well as this lower hatched region. So this kind of herringbone region is the losses if the firm does not produce. Now, how do we know that? Well, here's what we know. We know that if the firm does not produce, the firm will lose FC. We also know that FC, or fixed costs, equals total costs minus variable costs. Well, we could just multiply Q, we could divide everything by Q and multiply it by Q, and we'd be multiplying Q times TC over Q, which is AC, minus VC over Q, which is AVC. Or to write that another way, FC just equals Q times AC of Q minus AVC of Q. And indeed, that's exactly what this region is. For this Q star, for example, here's AC of Q. So let's call that AC of Q star. And this is AVC of Q star. So that vertical distance is the difference between them. And this horizontal distance is Q star. Well, multiply Q star by AC of Q star minus AVC of Q star, and we have fixed costs. So we can see that fixed costs, which are the losses if we don't produce, are strictly bigger than the losses if we do produce. So we should produce. Now another way to see this that cuts through kind of all the lines on the diagram is just to say, look, we've already incurred our fixed costs. The question for producing now is, do we cover the variable costs of output? If we cover the variable costs, then we make a little bit of profit, kind of quote profit relative to the cost of additional units, and this helps us pay back our fixed costs. So therefore we should produce if we can fetch a price above average variable cost. We'll see this again in a moment too. All right, I want to use this idea, both the idea of how do we choose the profit maximizing quantity of output, and this more recent idea about whether I should produce in the short run, to derive the actual short run supply curve for the firm. So here's the game, here's the exercise. Let's, to derive the firm's supply curve, let's consider a firm's optimal quantities of output, meaning its profit maximizing quantities of output, when the firm faces different hypothetical prices. What we're going to see is that the supply curve ends up being the marginal cost curve above the min of average variable cost. All right, so how do we see that? Well, up above, what I've done is I've just reproduced a diagram with average variable cost, average total cost, and marginal cost. And now we're going to imagine confronting this firm with various different prices and see what its optimal choices are. So, for example, suppose the price were P1. Well, we see where P1 intersects MC is here, but it's below min of AVC. So the optimal thing to do is to produce nothing. How about at P2? Well, it remains the case that the price is below the min of AVC, so the optimal thing is to produce nothing. When we get to P3, though, the optimal thing to do is to produce Q3. When we get to P4, the optimal thing is to produce Q4, and so forth. What are we doing? What we're deriving is the optimal thing to do at each of these successive prices is to produce the quantities along the marginal cost curve. If we represent these down below, what we've got is the firm supply curve. What it really is, it's the marginal cost curve above AVC. So literally, if we had a continuum of prices, we'd say it's this whole part of MC, the part that's below this dot. So again, the firm's short-run supply curve is its marginal cost curve above the minimum of average variable cost. Let's work a mathematical example, since these theories are all well and good, but it's good to be able to work a problem as well. So for a problem of this sort, you need to know the price and therefore the revenue function. So you'd be told here that the price is 36 per unit of output. Since it's a competitive firm, that price is constant, so revenue is just P times Q, or 36 times Q. Then you'd need a cost curve. So the short-run total cost curve for this firm looks like this. Now what's special about this? Well, this 100 is the fixed cost, and then we have some stuff that varies with Q. Let me also tell you that the marginal cost curve, and I would typically give this to you, the marginal cost curve, which is the slope of total cost, or if you're a calculus guy, the derivative of total cost with respect to output, is just equal to 20 minus 10Q plus 1.5Q squared. And again, I would give you that marginal cost curve. You don't need to know how to derive it, mathematically. Now, a point to make, we're trying to have this example correspond to our so-called usual shapes. And so the reason we've drawn a total cost curve that has a squared term, a Q term, a Q squared term, and a Q to the third term, is that if we want to get a U-shaped marginal cost curve, we need to make total cost cubic. Anyways, that's a detail that's neither here nor there. So how do we actually solve this problem? Well, what are we trying to do? We're trying to get an expression for the quantity, or we're trying to find the quantity that maximizes profit. Profit is total revenue, which is a function of quantity, and total cost, which is a function of quantity. We could write profit here as revenue, 36 times Q, minus cost, which is minus this whole business here. And we're looking for the Q where MR equals MC. So for us, that's just where P equals MC. So one way to do that is just to find an expression for MC, and we have that from the previous page, and we know what P is. So if we can just solve 36 equal this business, we will have found the answer. Well, even without doing it as an equation, what we could do is make a little table. We have Q here and MC here. And so we could just plug in and find that if Q were 1, MC would be 11.5 and so forth, and it falls to 6, 3.5, 4. What we're looking for is the quantity where MC equals MR, or P. We know here that P equals 36, and so if we draw in this demand curve for the firm at 36, and we draw in this marginal cost curve, we see where they intersect is at this point 8 units of output. You can also see it in the table. When Q equals 8, MC equals 36. And so indeed, 8 is the answer. That's the quantity of output that maximizes profit for this firm. There is another way to do this. If you like this other way, you could use the quadratic formula to solve this, and you'd find the same answer. I'll just, this is just for folks who prefer this method. What we had, if you think back, we had the following equation to solve. P, or MR equals MC, is 36 equals 20 minus 10Q plus 1.5Q squared. So the solution to this equation, the Q that solves this equation, is the Q that answers this question. And so that's what we're doing over here. And if you do that, you'll find once again that Q equals 8. Okay, last topic for this video. I want to talk about individual firm supply curves versus market supply curves. This is a little bit of a familiar idea. We're going to get the market supply curve from horizontally summing firm supply curves. So the idea is, these marginal cost curves above average variable cost for each firm are the firm's short-run supply curves. And so, for example, at some particular price represented by this purple horizontal line, firm 1 wants to produce Q1. That's its profit maximizing thing to do, and firm 2 wants to produce Q2. If those two firms are the only two firms in the market, then at that price, the market supply is Q1 plus Q2. But it's just this horizontal summation that we've seen before. For example, when we found market demand from individual demand. All right, what are the takeaways from this section? Well, a few things. First, a perfectly competitive firm maximizes profit by choosing output where P equals MC. And that's the special case of the idea that MR equals MC, but here MR equals P because P is constant. Another thing that's true at the profit maximizing quantity of output is that the slope of TC equals the slope of revenue. So that's just a corollary of this first point. Now, to maximize profits, a perfectly competitive firm, should produce as long as P is above the minimum of average variable cost. So somewhat counterintuitively, you might still want to produce with profits that are negative, because doing so leads to profits that are less negative than if you didn't produce. Next point is that the supply curve, the short-run firm supply curve, is the MC, the marginal cost curve, above the minimum of average variable cost. And finally, the short-run market supply curve is the horizontal summation of the firm's supply curves. All right, now we've got the tools for supply and demand. We did demand in the first module, and now we've figured out short-run supply. So let's put them together and do supply and demand analysis. Let's motivate this with a real-world example of ethanol subsidies and corn. So I have a picture here, and I'll just read to you a little bit. Young corn plants grow next to the Guardian Energy ethanol plant in Janesville, Minnesota. 5 years ago, the U.S. government projected that in 2012, ethanol production would use 30% of the nation's corn supply. Last year, it used 40%. So what's going on here? Well, we've got something, this use of ethanol, the use of corn to make a gasoline substitute, which has really driven up the demand for this thing called corn. So we can analyze this in supply and demand kind of diagrams, and indeed we have such a situation here. So we've got price on the vertical axis as usual, we've got quantity on the horizontal as usual. We have an original demand curve, D, an original supply curve, S, and then we have the ethanol subsidy going into effect, and demand shifts from D up to D prime. Now when that happens, we go from the original equilibrium, which occurred here and gave rise to this quantity and this price, to this equilibrium here, which has this higher quantity and this higher price. So the impact of this ethanol subsidy on this market is to raise the quantity consumed and to raise the price. Now these are real effects. I mean, they come out of the model, but you can actually see interesting impacts of what the model predicts in the news. So again, this is quite a recent news story. In the tiny tortilleries of this city, Guatemala City, people complained ceaselessly about the high price of corn. Just 3 years ago, 1 quetzal, about 15 cents, bought 8 tortillas. Today it buys only 4, and eggs have tripled in price because chickens eat corn feed. Now, what's going on here? Well, there's a world market for grains. This increase in demand in the U.S. because of ethanol is raising the price, which has repercussions all around the world, including Guatemala City. All right. Let's do an example problem. I mean, these kind of theoretical problems and even news stories are quite interesting, but it's also useful to be able to work a real problem. And so let's use our demand curve that we often use, P equals 100 minus Q, and so that's a market demand curve. Let's say the short-run market supply is given by P equals 20 plus Q. The first task is just to find the equilibrium price and quantity. And so what we're doing is we're, in the box it says here, we're trying to find the Q. Okay, find the Q such that the price on the demand curve equals the price on the supply curve. So what we've written here, this is the demand curve, and we had that before as P equals 100 minus Q. So indeed we're just putting in the 100 minus Q here, and the supply curve we had written as P equals 20 plus Q, and indeed that's what we're writing right over here. Set them equal to each other, and what we're doing is we're finding that quantity Q such that the price on the demand curve equals the price on the supply curve. So if we solve this through, 100 minus 20 is 80, add Q to both sides, we end up with 80 equals 2Q, or that Q equals 40. And then we can get the price either from the demand curve or the supply curve. So if we plug in 40 into the demand curve, we have 100 minus 40, which equals 60. It's actually a check on whether we got the right answer to do the same thing with the supply curve. So if we plug 40 into that supply curve, we have P equals 20 plus 40, and that's 60. So sure enough, that's a correct answer. Going back to the diagram then, all we're doing is labeling the relevant points. The intercept on the price axis of the demand curve is 100. The intercept of the supply curve is 20, and this equilibrium is the quantity of 40 and the price of 60. Let's take it a step farther then and integrate a demand shift. So what does it mean to have a demand shift? Well, remember the old demand curve was P equals 100 minus Q. So an increase, a shift that increases demand, well, one very natural way to represent that is just with a parallel shift. So let's just say the intercept goes from 100 to 120, right? So if it was 100, now it's 120. Let's say the slope stays the same. So we end up with this demand curve, P equals 120 minus Q. Well, we'd like to solve again to find the new equilibrium quantity and price. And so to do that, we just substitute 120 minus Q for what formerly was 100 minus Q. And so here, now, indeed, we have 120 minus Q, price on the demand curve, equals 20 plus Q, price on the supply curve. And if we solve it through, we get 120 minus 20 on this side, or 100, 2Q on that side, and so we end up now with a Q of 50. How do we get the price? Well, we can plug it in on the demand curve or the supply curve. 120 minus Q, or minus 50, is equal to 70. And so sure enough, let's go over to our diagram. The old equilibrium was here, quantity of 40, price of 60. The new equilibrium has a higher quantity, 50 now, and a higher price, 70. So Q and P both rise. We're not too surprised by that, but it's nice to actually see it worked through in the model quantitatively. So what are the takeaways here? Well, the first is, given a demand curve and a supply curve, we can solve for the equilibrium by setting the price on the demand curve, which I call PD here, equal to the price on the supply curve. So you set those equal and then solve for the quantity. Once you have the quantity, of course, you can plug that into the demand curve or the supply curve to get the price. Now it's also true, I say here or vice versa, because it's also true you could solve those two equations by setting Q equal to Q and solving for the P such that the quantities are equal. But either way, just solve those two equations together and you'll get a P and a Q, and that's the equilibrium. Second point, a shift in supply or demand changes the equilibrium price and quantity. So for example, as we saw here, when demand shifts out, the price goes up and the quantity goes up. When supply shifts out, then, which we didn't see, but you could work that out, you'd see that the quantity would go up, but the price, the equilibrium price, would go down.